Yeah.
I'll ask him.
Okay, guys, with some of the stuff that seems like you say you haven't seen yet, I figured I should probably show you some more stuff, okay? What do you see? Wire. Well, that's not a magnet. This is magnetizable stuff, okay? Basically battery. This is going to be constant or direct current. It's not going to change direction. But when you run current through coils of wire, what do you get? Magnetic field. That process is called magnetic induction. So we're going to make a magnetic field. The stuff that's in the center in here is magnetizable. It's not a magnet, but it is magnetizable. So not only will I get the field of the wires themselves, I'll get this stuff to become magnetized. If you're not going to pay attention, that's fine, but don't do it here. Go in the hallway or something. If you're not going to pay attention, that's fine, but don't do it in here. Okay? Go somewhere else if you're going to do that. Okay? Here's the idea. We took a paper cup and put a magnet in the bottom of it. Taped it in there. Okay? So that thing down the bottom is a magnet right there. Okay? Great. Attached to a rubber band, just for fun. Except more than fun. Because when I turn the current on, this is going to become magnetized, isn't it? This is already a magnet. And I'm not sure which way it's going to go. Let's see what happens. Oh, backwards, no problem. So we will take the leads and switch them, because that will do what to the magnetic field? Reverse it. So now we're going to get here. Last time the cup got pushed away, now it's going to get pulled. Okay. You see enough movement there? Does that convince you?
Yeah.
That's a pretty good movement. I could get it, yeah, I could get even better movement if I could reverse the current. Then it would get pulled and pushed rather than just pulled and relaxed. And yeah, we've already seen this, because that's how the speaker works. That's exactly how the speaker works. Okay? So what's in a speaker? Oh, there's a wire and a magnet. If you don't believe me, there's a magnet in here. That should be some pretty good evidence. That's what that thing is. There's a huge magnet in the back. Okay? There's no paper cup. Isn't that the cone right there? Okay, that's exactly how that works. So that's one thing to show you.
Where's that speaker from?
I don't know. Actually, I think maybe Mr. Houghton brought it in. I'm not remember for sure.
If it's a magnet, when you have to show that it repels one of the poles.
Alright, I've already shown you electric motor. We've already shown electric motor. What's in there? Yeah, it calls wire to magnet. Cool. We'll hook it up. And here's what, and we'll see how it works. Which is, you know, it's not bad. Come on. You can't see it spin. That's not too bad. And then I didn't realize I had another one sitting in a box unopened, and somebody opened it yesterday, and we looked at the difference between the two, and the thing that we noticed is that this one has 2 magnets. This one has 3 magnets. Wow. Yeah, I wonder if you get any better effect. I don't know, I guess there's only one way to find out. Would you like to be Aristotle or Galileo? Galileo. I should try it, didn't I? A little better, isn't it? Come on. I feel like it's going to take off. Just to make sure. Practical applications of that? Yeah, put some fan blades on the outside. That's how the fan blade works, right? Put something down, maybe something down here, and you call it electric drill. Put some beaters on the end of it and call it electric mixer, right? All that stuff. That's how all of that stuff works. All the electric motors power all that stuff. Here it makes a big deal about electric toothbrushes. Okay, fine. Dead true, I agree with you, but I think those other things were definitely better uses of it. So stronger magnetic fields generally have bigger effect. Definitely need that. Alright, so quick review here. If you ever run current through an electric or through a wire, what do you get?
Magnetic field.
Magnetic field in the shape of
Circles.
circles. And that's the first left-hand rule. Okay? That process is called magnetic induction. I hope you can say that in the quiz, because they're going to ask you that. Okay? But that's the first left-hand rule. Then we notice there's a second left-hand rule, which says if you have charged stuff moving in a magnetic field, that stuff exerts a force. And it just so happens that if they're moving this way, and the magnetic field is pointing this way, the force is this way. What you're supposed to notice is, hey, that's perpendicular to the way that they're already traveling. So if the electrons are trying to move this way, they get kicked off course. You're not hitting from the front or back, so you're not speeding them up or slowing them down. You're just deflecting them. It also happens to be perpendicular to the magnetic field. So the force that charged things experience when they exert in a magnetic field is always perpendicular to the way that they're moving and the magnetic field is. Why do they experience a force? We don't know. They do. You start with that, but if you can start with that, everything else flows from that. Okay? Everything does. One more time today, I promise. I won't do it again after today. Okay? Let's show how a motor works first. So, what'd you see inside a motor again? Magnet, good. North, south, see my big horseshoe magnet? See my coils of wire? Let's make it a motor. So let's attach these two to, how about a battery? Yeah. Outlet would be alternating current. Let's connect it to a battery. And so at this particular point, let's just say for the sake of argument, the electron's moving that way. Can you hold your hand the correct way?
Yes.
Can you hold your left hand that way? Yeah, at you. In a magnetic field that points from north to south, so the force on them should be down. Here's what's really important to me. They were moving along the wire, but they get forced perpendicular to the wire. These get forced down. Any guesses as the other side? Why? Because they're traveling this way and they get a field of point. So yeah. So, but again, either side, they're moving along the wire and they get forced perpendicular to the wire, and that's why it rotates. So this perpendicular, not if it was this perpendicular, wouldn't the wire go like this? That wouldn't do us any good. So luckily it's this perpendicular, and that's why it rotates. What do I say, down or up?
Down.
So as it rotates about a quarter of a turn, it's not connected to these electric leads anymore. They stay where they are, but as this thing rotates, they're not connected anymore. Okay, so there's no current. You'd think it would stop, but it doesn't because it has inertia. So it rotates again. Just by the time it starts to slow down, connects again. And that's what happens in the air. Okay? So we put in what kind of energy? Electric, and we got out mechanical. The electrons were moving along the wire, but they got forced perpendicular to the wire, and this process uses magnetic induction. The chart on the quiz tomorrow says motor, generator. Down the side it says energy transformations, it says physics principle, and it says direction of force on the electrons and movement of the electrons. So let's go with generator. Hey, what's in a generator? Well, it's a wire and a magnet. This time these don't connect to a battery, because why would you need a battery if you're going to generate electricity yourself? Now they're connected to a light bulb or a stereo or a bell or whatever, okay? Now we're going to crank it, and we've seen that. We're the ones that's going to turn it, okay? As we do that, let's just say we're cranking this way. Crank, 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 crank. At this particular instant, these electrons are moving down, aren't they? Down. In a magnetic field that happens to point from north to south. So the electrons are forced at me. Yeah, they get forced this way. These electrons are moving up in a magnetic field that points from north to south, so they get shoved this way. Well, that makes sense. They're moving this way, they're moving this way. I get these get shoved this way. And for this particular instant, it's connected. So we get a current. Quarter turn later, not connected anymore. Current shuts off. It's okay. We don't have to have it all the time. I mean, those lights aren't actually on all the time, are they? They're you just don't notice it. Quarter turn, good. Okay. So now we're putting in what kind of energy? Mechanical. Getting out electric. But you gotta understand, as we did this, at this particular instant, the electrons were moving down. What's more important is they were moving perpendicular to the wire, but they got shoved along the wire. That's different. And this process is called electromagnetic induction. That's what that chart looks like, so you've already got all that stuff. Right? All right. We went a little further with it yesterday. Is there anybody who wasn't here yesterday? Okay. If nothing else, just for you guys, and this is pretty cool. It's pretty cool anyway. So let's go back to this. I'm going to plug this into the outlet. is anytime you plug stuff into an outlet, what kind of current do you get?
Alternating.
Back and forth, yeah, okay. We already know if you just have a coil of wires and you just put direct current through it, you get a magnetic field. And the magnetic field looks like this, or this, one of the two. But when you alternate the current, the magnetic field goes like this, to this, to this, to this. Isn't that exactly the same thing as taking a magnet and flipping it around? Okay, so here's the thought process. Current goes back and forth and back and forth and back and forth, produces a magnetic field that flips back and forth, okay? Okay, so if we're gonna get a magnetic field that flips back and forth, why don't we just put this there? And now you have a closed loop of wire in which you are alternating the magnetic field. Faraday's law says if you do that, you're gonna generate voltage, which creates current, and because it's alternating, the current is actually alternating as well. Well, if you hook it up to a light bulb, you have current that's alternating. Look at that. Shove it down a little bit, works better. Why? Because the magnetic field is actually the strongest down in here, isn't it? I can't get these inside that, but the closer I can get, the better, and the better it works. Okay. And once again, we're not connecting anything. There's a bunch of plastic in here, the wires are not touching. Somehow, every time we do this, we end up with a couple of students that think, oh, we just connected the wires, cool. And why would I bother to do that? If I was going to do that, I'd just plug it in the first place. So we asked yesterday, that's really cool, why bother? Why bother is because the number of coils of wires are different. And we're supposed to know that the number of coils of wire is directly proportional to the voltage. So the picture that's supposed to be in your head at this point looks like this. Here's this magnetizable stuff, coat hangers. Bunch of coils down here that we had connected to the outlet. Bunch of coils up here that actually were connected eventually to light bulb, right? So inside a light bulb, there's actually two wires that come out. It might not look like it, but this brown wire right here, you can see there's a wall down the middle. There's actually two wires in there. There's got to be one for each side. You know, we just put the casing around it. Okay? But just to have some numbers to work with, let's just say there were 50 coils down here. And we know, since that's going to plug in the wall, we know it's 120 volts, don't we? You're kind of supposed to know that. Our outlets give you 120 volts, okay? Let's just say, for the sake of argument, we got 200 coils up here, because it does look like there's more of them, doesn't it? They're smaller, but it looks like there's a lot more of them here than there are down there. So we change the coils by a factor of 4. Well, if they're directly proportional to each other, then the voltage up here has to be. Once again, cool. So what? Again, real quickly, the so what is you have these things outside your house, and that's exactly what's inside them. Your house is expecting 120 volts. Those lines that go across the country, they're not at 120 volts. If that's the case, you'd probably fool around with them and be all right. Those are more like hundreds of thousands of volts. So here's the idea. These things have huge voltage and little itty-bitty currents. Your house has a pretty big current and a pretty small voltage. And when you take voltage and multiply it by current, you get power. Power is current times voltage. The idea is you can't change the power. That would violate conservation of energy. So, finish. If we just happen to know the current down here, let's just say it's 8 amps. If the voltage went up, the current has to go down by the exact same factor of 4. So the current up here has to be 2 amps. When you look at it, you go, oh, 8 times 120 happens to be 960. 480 times 2 happens to be 960. When you multiply them together, you have to get the same answer. So just don't be one of those people on the quiz that picks, oh yeah, the voltage gets bigger and the current gets bigger. Because I guarantee that's one of the choices. That's not true. You can't do that. That violates conservation of energy. They can't both get bigger and they can't both get smaller. So this whole thing is called what? A transformer. Uses down here, since alternating current produces a magnetic field, that part is called magnetic induction. But an alternating magnetic field that produces a current is called electromagnetic. So it uses both. wish I did. All right, we're getting close.
3 years, a couple months ago.
All right. Yeah, yesterday. With my classes, we saw this 2 weeks ago, and we said we we're going to explain it. Now we're finally ready to explain it. I just got to check. Did you guys, Mr. Shoemaker's classes, see this?
No.
Okay. So let's take something that's not magnetizable, right? I agree.
Oh, yeah.
Just falls right through, doesn't it? Okay. Let's take something that's very magnetized. The first time I saw somebody do that, the guy held it like this, I was firmly convinced he had a magnet in the palm of his hand. That's not true at all.
What about your ring?
Good question. Okay, what about my ring? Good question. I'll do the other hand. In fact, how about like this?
What about your fingernail?
No, I don't. Did you know how to explain this? See the coils of wire? That's all this really is coil after coil after coil, and it's pretty thick. So it conducts electricity like crazy. Is it magnetizable? No, we can't magnetize it. We could even put it inside the magnetizer, which is full of coils of wire, which produces a strong magnetic field. It wouldn't do any good. Oh, wait, I got it. What's the magnetic field strength inside here right now? Yeah, whatever the earth is, it's not real strong. As soon as you drop this in here, aren't you changing the magnetic field strength? And it's closed loop. It's not like that one that I cut the other day. It's closed. As soon as you do that, don't you generate current? But I'm not doing this with it, so it's not alternating current. It's just direct current. We're supposed to know when you put current through loops of wire, what do you get?
Magnetic field.
And not a changing magnetic field, a constant magnetic field, which happens to oppose this. And that's all it is. That's all it is. Yeah, it's magnetic induction and electromagnetic induction both together, all over again. Okay? I would say when we pass this around, why don't you keep it away from your phones and keep it away from your calculators. But it's fun to kind of watch it. Just we've had people say, "Oh, I know, it just barely fits in there, so it's just friction." Now there's enough slop in there. It's not just friction. Okay? There's enough slop. There's enough play in there. It's not friction. Okay? Yes, she's done Okay, last point.
What do you need for? We like took place the smaller.
Especially if you're way far away. You got a rubber band and a slinky, and finally in the bottom, I have a magnet. I needed it to be able to bounce, basically. You can't see, you can understand it, whatever. There's a magnet on the bottom, okay? Just about in the mouth of lots and lots and lots of coils of wire, okay? I just want to have a connection, so I'm going to clip on both of the leads of this. I'm not going to plug it into anything. I'm simply going to connect over here to another set of coils of wire. So all I've really done is connect two coils of wire. That's not what we did in the transformer, right? In the transformer, I didn't connect the coils of wire at all. Now, all I've really done is connect two coils of wire, okay? All right, here's what I'm going to do over here. What's the strength, magnetic field strength inside this coil of wire? Yeah, wherever the earth is, that's it, okay? Could I change the magnetic field strength in there? I could. In fact, if I went like this, wouldn't it produce a current that alternates? Wouldn't you produce a current that alternates?
Yeah.
A current that alternates produces an alternating magnetic field, and there's a magnet right there waiting to feel that effect. So let's just see. This is not part of the setup at all right now. What do you think it is? It's not bouncing wildly, but do you see any movement whatsoever?
Yeah. Oh, now it did. For sure.
Yeah, you did. All right, so I played around with this in statistics yesterday when we get here. I started doing something with this. Oh, come on. Strong magnets, darn it. Stop being so strong. Just shake it back and forth.
1
maybe I wish it would jump up and down a foot, but is that at least some evidence that's moving?
Yeah.
Okay. Again, cool. So what? There is a way to get a magnet to flutter back and forth like that without shaking it back and forth. Especially if you put a paper cone over here and went, ah, and you could make that paper cone flutter back and forth, which would make the magnet flutter back and forth.
Which then in turn causes the other magnet.
Which makes the other, yeah, this is a microphone, right? This is a microphone. Ah, it's also called a telephone. You speak, it makes this flutter back and forth. The other end has a paper cone which flutters back and forth, and they put it next to their ear.
So like on the old telephones, you really don't need like electricity.
Yeah, you don't need electricity for the phone. Did you ever notice that? If you have a landline phone, it still works when the electricity goes out. It's not dependent on that. I mean, can you picture, could I make longer wires and take this down to Mrs. Ford's room and I'll stand there down and do it and you'll know when I'm doing it? Could I take it down to Higgs' room and do it? Yes. Could I take long enough wires and take it to Dan's room? Yes. So, that's not how cell phones work, but that's how landline telephones work, and that's how microphones work. And so, what's that? We're not ready for that. Anyway. So, I wish I could get a better bounce. But in a telephone, how far does the thing have to move for you to notice? It's not that far. It's not like a phone going bang, 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 right? It doesn't have to be that much for you to hear. Okay? Question? James?
I don't want it.
So it's got to start with this, and then we'll take care of the cell phone stuff later. It's got to start the same way. So I wish I could get better. Okay. So the quiz looks like 6 or 7 multiple choice questions. I say questions about Faraday's law. Hope you can say it in words. Back, draw a picture, explain how such and such works. There's going to be pictures of magnetic fields. You draw that stuff. And that big chart we talked about. You know what it looks like. And the practice quiz to get you ready is right here. All right. This is about right enough time to get done with it. Good luck on the quiz tomorrow. We did say you're not going to be here, right? Okay. So we made the decision you don't get to use your own periodic or your own formula pages. Unfortunately, too many people have violated that. No paragraphs on their formula pages. So my classes, I don't think you need anything more than this. We already wrote everything I think you need down on the student's board. So I'm sorry, but you can't use your own formula pages tomorrow because too many people have changed it. And everything I can't remember page. Right?
No.
Grab practice quiz, get you up. Let's stay here.
Yeah, we'll stay here.